So we will just walk through like how does Cassandra, possesses the reads and writes inherently, and we'll talk about apart from the various things we talked about, Cassandra components earlier. Now we'll try to understand what exactly the different processes running. So when we have written the data already, so what does happen apart from that? So how does Cassandra optimizes itself, and how you can force Cassandra to optimize a particular thing. So we'll talk about different things. Um, Okay, so there is something called System Keyspace. So as you know, guys, in RDBMS world, right? So we have something called system tables, wherein RDBMS maintains the metadata about other tables. So if you create a table, you say this is the column name, this is the data type. So where RDBMS stores that information? So it gets stored in system tables only. There are certain tables to store the information about tables, the other tables, and certain tables to store the information about the primary indexes that you create or whatever indexes you create, right? So that's what happens in RDBMS. Similar way in Cassandra also we have something called system key space to store the data about other key spaces. So it stores the metadata about cluster and also the some operational data as well. Okay, so that's what a system key space means. And system key space stores metadata for the local node and as well as the hinted handoff information. So what happens is, what is hinted handoff information? So let me just take a moment and explain it. So what happens is we have a node of say 20 clusters. Sorry, we have a cluster of 20 nodes. Okay, and if one of the node goes down, right? So suppose one of the node went down. There was some failure, so some hardware failure with that node, or some small failure. You wanted to do some maintenance, and you have to bring that node down. And now, like, what happens with the key range that was associated with to that node? We learned about it, right? Partitioner decides the key range for each node, right? So partitioner decides where the first primary copy of the data will go, right? So it will go. It is supposed to go to that particular node. What if that node goes down? What will happen to that key range? So what happens at the time is, so the nodes, other nodes in the cluster will start storing the data that was supposed to go to the node which has went down. Okay, so it will start storing the data with the hint associated. So suppose we have three nodes, node 1, node 2, and node 3. Okay, and there is a key, like say key equal to 5, that was supposed to be written on node 2, and node 2 went down, node 2 is not available. Now node 3 will take up that row, that data will be taken up by node 3. Okay, and but it will store it with a hint. What will be the hint? Hint will be like, I have to transfer it back to node 2 when it comes back. This data belongs to node 2. This is the hint it will maintain internally. So as in this point, just learn about it. Just have a plain understanding. So what is hinted hand of information? The hint stored by the other nodes to basically to basically mark the data as since it belongs to some other node, so they just want to mark it somewhere, so they just maintain a hint. So that's how they do it, right? So then in the metadata that we store in Cassandra system key space, so what do we store? We have the nodes token. Nodes token is nothing but the key range. So we store the first value of the key range as the nodes token. So if your node is supposed to take the values from 1 to 10, right? So nodes token will be 1. Okay, so that information is decided by partitioner when we start the cluster, so that's decided by the partitioner itself. Okay, so then we have the cluster name also stored under metadata. We store what is the cluster name. So in case there are two nodes and the cluster name is different, and you try to basically bring them in the same cluster, they won't be able to. The cluster name has to be same always. Key space and schema definitions to support dynamic loading. So it will have the metadata about different key spaces and different column families that you have, so that you can support dynamic loading, right? So you can create any new structure also. If the structure is already there, you don't need to create it and all the stuff. So it decides depending on the schema definition it stores. And there's something called migration data. So what is migration data now? So migration data is nothing but, like, if you change something in a key space, suppose you change the replication factor from 1 to 2 or 2 to 3, that information is stored under migration data, right? So any configuration changes or any changes made to a key space, those changes are stored under this migration data. Okay. And the sixth one, like the fifth one is whether or not the node is bootstrapped. So what is bootstrapping? I think I explained you. So just let me just take a moment to explain again. Anyways, we will be covering it in detail in the next slide. So bootstrapping is when you bring a new node to the cluster, you want to add a new node. So what happens is you add that new node. When this new node is added, it is not aware with the cluster configuration. It doesn't know how the cluster looks like. That node is, we call it as dumb node. The node doesn't know anything about the cluster. It doesn't know what all key spaces it has. It doesn't know whether like what are the different configuration have been set on the cluster level. So it needs to get ready with that thing. It needs some time to get acquainted with the cluster. It needs to get time I mean, to basically to get all the configurations that we have made in the cluster. So what happens is when a node comes up, Cassandra has a process called bootstrapping. So once a node is bootstrapped, it starts copying the data from other nodes. So which other nodes it will start copying the data? So other nodes we specify as seed nodes. So if we have seen in Cassandra YAML file, we have something called seed node. So we can declare a list of nodes as seed nodes. So seed nodes are not something like master nodes or so. They are just the seed node. We have declared few of the node at seed node, which tells we can pull the system key space and all that information from that particular nodes. So they have an extra responsibility of basically um, of like being available in case a bootstrapping node basically asks for some information. They should be giving that, but there are no master nodes. I mean, in case the boot I mean the seeds nodes are not available, the node will contact any other node. So but that doesn't happen usually. We have like we can declare any number of nodes at seed nodes. So normally we have 3 to 4 nodes at seed nodes, so that the other node that comes up, we add when we add new nodes, they will be able to get the data from those nodes. Okay, so that's what we mean by seed nodes. So the bootstrapping also is clear. Anyways, if it is not, we will cover it in detail in next slide, so don't worry about it. Just have an idea. So since these words were mentioned here, I want you to just cover in a some like I just wanted to give you guys some understanding about it. Okay, so system key space cannot be modified and edited by us, which is fine, right? I mean, it has all the data, all the crucial data that Cassandra cluster must store, so it should not be editable. So that's what I mean. The same thing happens in all other systems as well. If you see in case of RDBMS also, we don't have rights to edit system tables. So system tables is something, system key space something maintained internally by the Cassandra user. Cassandra itself maintains it. Nobody from outside has the access to do anything. Not even an admin can change it. As simple as that. Okay. So this was about system key space on a higher level. We will go through and talk about. I'll show you how does system key space looks like at the end of the session. Okay. So as we talked about system key space, so system key space has two column families. Okay, and system key space has two column families. One is schema column family. Schema column family basically will hold the schema definition and user key space data. I mean, all the metadata about other key spaces are stored in system schema column family. And there is second column family which is called as migration column family. Just a minute, guys. Which is called as migration column family, and it records changes made to the key space, like config changes we make and everything. It gets recorded under migration column family. So these are the two major column families, or the two only column families I think in system key space. So so it has all the crucial information, and system key space should be available all the times. Okay. Yes, in Oracle it is sys, right? That's fine, Manisha, that's good. So but the same concept is there in SQL Server as well as other RDBMS. So I don't exactly remember the names, so probably you guys go and check it after the session. Okay, so there's something called peer-to-peer. So as we said earlier, so in Cassandra we have peer-to-peer architecture. There is no master-slave architecture, right? So every node is equal. So every nodes are similar. They do the same job. There is no there is no difference in the functionality of each of the node. Okay, so each node is almost similar, not almost, it's actually similar in terms of the processing it does. Okay, so when we add a new node, basically what happens? It gets bootstrapped, right? And it basically serves the same kind of processes which are being served by other nodes. So probably when you add a new node, at that particular time the new node will be doing some other stuff like bootstrapping and all that stuff. But once it is bootstrapped, it is good to serve all the requests made to Cassandra, whether read or write or whatever internal balancing and all. So then it behaves like almost like all other nodes. There is no special functionality or anything associated with any of the nodes. So how does equality help? So why we have chosen equality over master slave architecture? Equality improves general database availability. So if you have seen in case of Hadoop, MongoDB, there is master slave architecture, right? But in here in Cassandra, unlike Hadoop, we don't have any master slave architecture. So that's why the availability increases. So there are no single point of failure, right, Ranjit? As you mentioned, there are no single point of failures in Cassandra, and this also helps in scaling up and down easier. So you can add new nodes, you can remove the nodes anytime. So there is no disruptions made to the cluster. Cluster will always be up and running while you add and remove new nodes. It might be slower when you add more number of nodes or remove it. At the time after removing it might be slow, but there are no disruptions. So the user request will be served. So there are no disruptions at all. So it is done in an online fashion. The overall cluster health is online when we scale it down. Okay, so these are the different architecture layers in Cassandra. So probably these are, I mean, if you see Cassandra architecture internally, there are no differentiations like core, middle, or top layer. It is just for the logical purpose and to explain you guys. I mean, you won't see this kind of distinction like anywhere else. Okay, so the core layer has something called messaging service, gossip protocol, cluster state, partitioning, and replication. So messaging service is nothing but how do different nodes exchange different messages. Then we have a gossip protocol. The nodes basically talk to each other using gossip protocol and all that stuff, right? In middle layer, we have something called Commitlog, memtable, SStable, indexes, and compaction. Sorry, guys. And in top layer, we have Tombstones, hinted handoff we already spoke about, read repair, bootstrapping, monitoring, and admin tools. So we'll talk about each one of them in detail today. So first comes commit logs, mem tables, and SS tables. So what are commit logs? So commit log basically helps in crash recovery. So when you give a write request to a Cassandra cluster, what does happen to that write request? Okay, so write requests are first done on commit logs. So write request will be made on commit log. Okay, so commit log is nothing but a file on hard disk. So if you have seen, it will be under varlib Cassandra commit logs. Varlib Cassandra commit log, that will be the directory of commit log storage by default. You can change it if you want to, but that is fine. That is absolutely fine with Cassandra. So when you make a write request, the data goes to commit log first. It's almost same to the bin logs in case of Oracle. We have something called bin logs or all right in Oracle. The write where that should do it goes to bin logs first. So in case of Cassandra, it goes to commit logs. And once we write in like commit log, once the data is written in commit log, Cassandra writes are deemed to be successful. So what does happen when you submit a write request? You submit a write request, writes go to commit log, they are appended to commit log, they just get appended. There are no updates. Okay. So you just add the commit log, you just add the data in commit log, you come back and say, hey, your data writes are successful. This is what happens while writing the data to Cassandra. Once the data is written to commit logs, and then it is written to something called mem tables. Mem tables are nothing but some memory sort of tables. It's a memory data structures, some data structures present in memory, which takes the data and stores it in memory. Okay. Again, it is a append only operation. There is no update. I'm not talking about any update as in this point of time. There are no updates. Okay. So what happens is mem tables, we have a threshold associated with each mem table. We say okay, the mem table for this column family can be say 1000 MB, or let's say 100 MB. So once mem tables reaches that size, so suppose the data written in mem table reaches 100 MB, then that mem table will be flushed onto hard disk. So I mean, the data will be written to hard disk once it reaches that threshold limit, and that file in hard disk we call it as SStable. The full form of SStable is sorted strings table. Okay. So SStable, what will happen is data will be written to Commitlog first, then it goes to mem tables, which is the first memory data structures, and basically it's the first data structure the data goes to. Commitlog is not a data structure; it is a file. Mem tables are the first data structure the data goes to. Okay, and then when mem table reaches the threshold limit, the data is flushed to SStable. Okay, so guys, this flow is clear. I just want to make sure this is clear before proceeding to the next topics. Even to like, I want to explain this thing in detail, so I just want to make sure the first step is clear or not. Guys, can you respond if you are clear or not? What are mem tables? Mem tables are nothing but memory tables. So there is some data structure defined in memory. Okay, and data just goes in memory. That's it. I mean, there is no other definition to mem table as such. It is some kind of data structure defined by Cassandra, which can take up the data for some of the column families. Okay, so you can actually assume the mem table to be kind of a table structure, kind of a column family structure. You can assume it to be. It's a custom data structure that Cassandra has created. So when write and update happens, what happens? It goes to commit log, at the same time it goes to mem table also, or from commit log it goes to mem table. It's the same thing. It happens at the same time actually. It rise to commit log, then it rise to mem table. Okay, and then some data goes from commit log to mem table also sometimes, right? To just match it if the data written here and data written here are same or not. Okay, this is what happens in a commit log and mem table thing. Then from mem table, when it reaches the threshold size, data gets flushed to SStable. So there is one SStable 1, SStable 2, SStable 3, so on will be created, right? And then later on there is a process that we can manually trigger, which is called compaction, that can combine these two tables into one, and then these two tables are deleted because these table cannot be changed. So we cannot say okay, put SS table into SS table 1. We cannot do that. We have to create a new SS table from these two SS table reading. We just read those SS tables and create a new SS table, and then we'll discard these twos. This is what happens when we do compaction. We will talk about it in detail. How does compaction basically works? So when you read the data, you have to make sure like whatever like updates are there, you have to just read the latest data. You have to make sure that, right? Suppose let's take an example. For a users column family, you updated the city from Bangalore to say New York for one user. Say for Kunal, you updated for from Bangalore to New Delhi. Okay. So the Bangalore data will might be there in SStable since it was old data. It is there in SStable. It can be here also, right? So once you merge them in SStable, this one, there might be some new tables also that might have created from M tables, right? So this is how it happens. So there might be multiple SStable at any point in time. So you will reach every SStable, all the SStables will reach. Sorry, you will read, and then you'll go to mem table also to read the information. So first you'll check in mem table. If you want to read the city information about Kunal, you'll go to mem table. If it is not there, because mem table has the latest copy of the data, right? If it is not there, then it will go to SStables. This is all the SStable it will search then. So if it gets from mem table, we are good. We know the data is there in mem table. We will take that one because memory reads are very fast. So we will prefer reading from mem table since it has the latest data also. If there are any updates, it will make sure it will take the data from mem table only because it is supposed to be the latest one. Right, guys? So that part is clear. How does it like updates the data while reading? So what it will do is, so it will so suppose there were three cities. Let's say Bangalore, New Delhi, and then I came back to Bangalore. Let's assume that. Okay, and everything has been flushed. Everything has been flushed. There is no data in mem table as in this point in time. So say Bangalore went to SS table 1, Delhi went to SS table 2, and the old Bangalore. So sorry, let me start it or like all over again. So the first Bangalore, the first city equal to Bangalore went to SS table this. This is the old SS table, let's assume. And then Delhi went to SS table 1, and then Bangalore went to SStable 2. This is how my updates happened. First it was Bangalore here, then Delhi, then Bangalore. It will be the data will be stored thrice. The same data will be stored thrice, but there is no need to. We know that, but this is how Cassandra makes sure the writes are fast, because at this point in time it just appends it. While reading, we will make sure we will read from all the SS table and we will do the update. We will just take the latest record. We will just pick the latest record, which will be Bangalore only. Since I updated the city from Bangalore, Delhi to Bangalore again, it will be Bangalore only. SS table 2 will have the data Bangalore. It will read the data from all three SS tables and it will give me the latest record. So now you guys tell me how will it find which one is the latest record among these three record it might have got from SS table. This table it might have got city equal to Bangalore. From here it got city equal to New Delhi. From here it got city equal to Bangalore. How does Cassandra decides which one is the latest record? So guys, please respond. I've got couple of responses, both very interesting. So I just got couple of responses, guys. Please respond. Just think anything. I mean, just fine. I mean, just go ahead and let me you answer. Let me know your answer. I mean, it can be wrong also, but it's fine. I just want you to develop that kind of thinking environment. So, name you say three. What does that mean? Three. Can you just elaborate it? What does three means? Yeah, no, but I'm asking how it will come to know which one is the latest. We know the Bangalore one is latest. Bangalore one is what will be returned to us, but how it will make sure it is the latest one? Which metrics it will see to like get that information? It will have to know, right? Cassandra somehow it needs to do that conflict mechanism in place. So what happens is most of you have answered it correctly. And Ranjit said, based on latest SS table. No, Cassandra doesn't know which one is latest SS table or not. It doesn't go that way. So what happens is there is a timestamp associated with each column, as you guys might remember, right? There's a timestamp associated with each column. So that is where the timestamp is used. It is being used at many places, but this is the one place where it makes most sense doing updates, deciding which is the new record, right? So depending on the timestamp that is there with the each of the column, it will decide which one is latest. Okay, are we clear with this, guys? Are we good with the write process and read process? So is it interesting the way it happens? Okay, guys, everybody saying yes, yes. It is quite different from what used to happen in RDBMS world, that boring, writes and all. But here it is little, different and it interesting also. Okay, so everybody's saying yes, yes. So probably they are interested. Yes. Okay, so basically I'll go ahead and show you SStables also. How does the SStables like look like on hard disk? Don't worry about it. We will see Commitlog also. Everything we'll see. Yes, Srinivas, a very good observation you have made. Very good observation. Srinivas says it is interesting, but looks like more space intensity intensive. Yes, it wastes a lot of space doing that. It makes your observation is 200% correct. Space is wasted, but when we trigger something like compaction, we retrieve the space. There is a process that we have in place to retrieve the space also, which is again resource intensive. Like it takes a lot of resources while doing the compaction, and while the compaction is going, the performance degrades a little bit, not much, a little bit. So whereas this is space intensive, to remove it, we run something called compaction, which is resource intensive. I mean, we will talk about it in detail, but a very good observation that you made. I wanted to just tell everybody also. Data, if you see, guys, data is duplicated again and again. It stores city equal to Bangalore, city equal to New Delhi, city equal to Bangalore again, which doesn't make sense. We just are interested in the latest city. Why we should store the previous city as well? I mean, it doesn't make sense because the previous city anyways will go down while doing compaction. Anyways, it will be removed. It is not a permanent storage. There might be some requirements wherein we want to have the history permanently, but this is not the way to do it. So that's how Cassandra wastes a lot of space, but there is a way to retrieve it also. We will talk about it. So now we talk about hinted handoff. So as I said earlier, so what is hinted handoff? Hinted handoff is nothing but in case a node goes down, the other nodes will get the data that belongs to that particular node and it will maintain a hint saying, okay, I have to transfer it back when the bad node comes up. Okay, when the node that is down, it will come up, the other nodes will have to transfer it back. So it's a kind of a post-it note that contains information about the write request for the bad node. It will just maintain a note associated with that particular record it's taking as a write onto the I mean the node which where it doesn't belong. Actually it will say, okay, I'll take it up, but you have to take it back when you come online. So this is how the information is being shared using maintaining a flag using hinted handoff. Okay guys, so can you guys think of any issues or any problems that can be there because of this hinted handoff? Any issues that you can think of? I mean, which may lead to if you use hinted handoff in our cluster. There can be some issues. So let me tell you a few things. There can be some issues with hinted handoff, but I would like you guys to think about it and like let me know what it can be. So there are so many people. I hope to get at least one correct answer. Guys, please give any thinking process that you might have in your mind as of now. Just give anything you have been thinking. It might be correct also. It is very basic thing that can happen. I mean, known is not something that we haven't covered or anything. Just think of a cluster and see hinted handles being transferred, and what will happen eventually to the hinted handoffs and all the stuff. So just try to imagine it. No. Okay, so just let me just take it up instead of waiting for the answers. So let's assume this. So this is your cluster. This node went down. Okay, and now there is a key P that was supposed to go to this. So W and A or probably one of these will take up the data for WP key P. Okay, so hint will go to the one who will take the data for key P. Hint will be associated with that. And suppose now did they, I got a response. Hinted answer, it will goes down. No, that's not the correct answer. Srinivas. Hinted handoff is a service. I mean, it's not a node or anything. It's a kind of a service running on Cassandra. It cannot go down unless or until you disable it. Okay. So once a node comes up back again. So suppose T came back again. So W and A will start transferring all the data that they have for T immediately. So immediately a node T is back again. So it will start transferring the data. So there can be a network congestion in that case. Too much of data flowing from W and A to T. If there were so many writes that belong to T that happened in between, then it is a case of I think we need to pay some attention, because at the time every node will start transferring the data to T again. So which is a very bad scenario, and your Cassandra cluster performance will come down because three nodes will get busy. W, A, and T. Three nodes will get busy. Even more than that. I mean, whenever if there is too much of data, probably every node may have some hinted handoff stored for T. Any nodes can store it. So you may end up every node having some part of it. So everybody will start transferring to T when it comes online, and which is a case of like a performance degradation. We should be so people in open source, they have been talking a lot about a hindered handoff. If a node goes down, there's a way you can disable hindered handoff. If you disable hindered handoff, the new key range will be decided for each of the node with the partitioner. So it will assume the like cluster to be 4 node instead of 5, and it will rearrange the key space, the key range that you have. It will rearrange it, and then a node comes up, then again the key range is redecided. So that's how it is done when the hinted handoff is disabled, and people have been talking a lot about it, and now Cassandra has given this option of disabling it. So you can disable it, go ahead and disable it, that also works fine. Okay guys, so the next topic is read repair. So let's wait for some more time to discuss this. I want some more time, so I want to cover some other topics before we discuss this part. I'll come back to this slide. In case I don't, please remind me to do so, because last class I forgot to come back. I kind of I came to know, I kind of forgot about it, and then at the end only it came to my mind, so then I explained it. But anyways, do remind me in case I forget. Compaction, we have been talking, I have been mentioning this word a lot. Compaction, what is compaction process? So compaction is a process of freeing up space by merging large data files in terms of SS tables, in form of SS tables. It basically merges different SS tables into one. Whatever SS tables we have, it will merge. Okay. So what is the merge process? It will merge the keys. So all the keys that are there in all the SS table, it will merge in one SS table, and the columns are combined. Columns are combined. I mean, there might be one column written in one SS table, other column written in other SS table. The column will be in one row key. Okay, it will basically have a kind of a same structure as a column family, and in Cassandra it will have the same structure, one row key and associated columns with that in that one place. Okay, and tombstones are discarded. What are tombstones? Tombstones are something like soft deletes. You delete something that happens in like Cassandra. The deletes that happen are the soft deletes. We will talk about it in detail. So what are soft deletes? I mean, you might be knowing what are soft deletes. We don't delete it actually, we just mark it as deleted, but the data resides there physically. So we will talk about it. It's a kind of a soft delete process. So if during compaction, tombstones are also discarded and a new index is created. We have to create the index on row key, right? So a new index is created for the SS table. Cassandra supports multiple type of compaction. There is a read-only compaction that happens while reading. You're reading the data and you do some sort of like compaction, right? I mean, you kind of discard some data while reading it. You kind of pick only the latest data. That's also kind of a compaction, right? We call it a read-only compaction. It doesn't change the underlying SS tables. There's something called major compaction. Major compaction is nothing but when you actually do a key space level compaction. All the column families under that key space gets compacted. That's what we call a major compaction. And a minor compaction can be you are doing it on a particular column family, then you can call it as a minor compaction. So you should always like, since compaction, when compaction happens, how does it happen is what does different processes that run compaction basically. So if we have two SS tables to be combined, there were two SS tables, SS table 1 and 2. Compaction will load those SS tables into memory first. So the SS tables will be loaded to memory first, and then the compaction is done. It's a kind of an in-memory process. So now you can imagine doing a compaction like process, that too in memory, how costly it will be. It is a costly process, it is a time consuming process. So that's why we set the priority to be low. So the compaction thread that runs on Cassandra, we set the priority to be low. This is the way to do it. It is one means high priority, you can set it to be 0.2 or 0.3. We set it around 0.4 in our Cassandra cluster. If compaction is running, the priority is low. The resources allocated to compaction are like less as compared to the other actions. So the other action who have a more priority will be given the priority over this compaction, because compaction is something a kind of a backend maintenance and all to basically free up space. Of course, reads will get faster with compaction. Reads will be, because you are combining the data, you are removing some data also. So the data that you might end up scanning might be less. So reads also get faster with compaction after compaction. So this is a like visualization of how does compaction happens, and it will also give you idea how the data is stored in SS tables. So suppose you made a first entry of a particular row key. You said first name is Nathan, last name is McCall, and the city is San Diego. This was the first entry made, and it went to SS table 1. This is SS table 1, and then you updated the city to be Austin. Then suppose that information went to SStable 2. Then you updated the first name to be Nate. It went to SStable 3. This is how the information is actually stored in Cassandra. Different SStable will store the information in this way, right? So this is the representation of the SStable storing the information. Now, if you run the compaction, this light blue color box that you see on right hand side, this is what you see in the final SStable. So the three SStable will be loaded to memory, and then the compaction will be done, and this is how it will store the data. It will store the first name to be Nate, which is the latest name, latest first name, and the city is Austin, which is the latest city. This is how the compaction will run. Fine, guys, you understood what compaction actually is and how does it run. That part is clear. Okay, so this was about compaction. Let's go. And compaction can be manually triggered as well. Most of the times it is like you can either schedule it or you can manually trigger it. So depending on when your cluster is not being so much utilized, it is at some downtime. I mean night time or so, you can do it. Since it's a resource intensive process. We talked about something like Bloom filters. We said Bloom filters are, I mean, every SS table on hard disk maintains a Bloom filter associated with it. It maintains a Bloom filter. Bloom filter is nothing but a in hash comparison of the keys. It basically maintains the cache of keys. Sorry, hash of keys somewhere. Okay, it's a special kind of cache basically based on hash functions. It maintains the cache of the keys. Okay, it is done for the quick lookups and search. Since everything is in memory, so it is very fast also. Since memory reads are always faster than disk reads, so it happens all in memory. So as I said, Bloom filter can give you false positive, but there are no false negatives. There are a certain percentage, very less percentage of false positive. Okay, and and there are no false negative. If it says the record doesn't exist, that will be sure. If it says record exists, that might be either true or false. But the percentage of being false positive is okay. So you use this scenario, use this Bloom filter where you want to do a negative search. You want to search the components where this field doesn't exist. You want to search something, you want to like, if I mean, let's take an example of Google. You want to maintain a Bloom filter on different web pages where this keyword does not exist. I mean, it's not a right scenario, but let's take a scenario. Then you can use it. If you want to just search the pages where this information is not there, then you can use Bloom filter. It may, what will happen is it may basically avoid, probably, I mean, the correct number of results might be 4, but it will return you 3. But the 3 that have returned will be correct always. False for the false negative search will be correct always. So this is how it happens in Bloom filter scenario, in SStable scenario. Let's assume we have 5 SStables, okay, and we are writing or reading or something we are doing. We are reading, let's say. I mean, when we write the data, it goes to different SStables, and every SStable has millions of records, millions of rows to be scanned in case you want to read a row key. Now you want to read a particular row key. Say you want to read row key equal to 100. So it will go to first SS. For the first option is it will scan all SS tables. It will just go and scan all SS tables, five SS tables that used to happen prior to, I think, 0.6. That was when it was, I think 1.0 or 0.6 it when it was introduced. Before that it used to happen that way. While reading it used to go to all the SS tables, and millions of rows it used to scan, which is not the correct way of doing it. The, then you set up Bloom filter, you go to SStable 1 and you don't search SStable 1, you search the Bloom filter. You go and search Bloom filter which is in RAM, which is in memory, and it says false. We got four false and only one true, so in that case we'll go to the last SStable only. It might return you the result saying okay, this is the value that you actually requested for. It might come back and say okay, the value is null because that record doesn't exist here, but you end up scanning lesser number of SStables. So this is what is done in Bloom filters. This is what we mean by Bloom filters. So are you guys clear about it? How does Bloom filter work? So like anybody who has doubts regarding Bloomfilter, please feel free to ask, or any doubts in compaction or any process we discussed till now, please feel free to discuss. We have a lot of time left, so and we have a very little to cover. Just go ahead and ask your question, because this is something that you need to be clear about each and every aspect of it, because this is how you will decide what to tune and what not to. So where you need to spend your time while tuning the cluster, doing some performance enhancements, this is how you decide, right? So I would request you guys to just go through it, just have a look, just think about it, and in case you have any doubts, any clarity you want me to cover it again or something, please go ahead, we can do that. The compaction example you showed, is that read only compaction? No, it can, I mean, that was the overall concept of compaction. So how does compaction runs? So the example that I show, it shows it will return the latest record only. The same thing will happen in read only as well as write. So read only, I showed you a I showed you a write, I mean the major compaction, because it's creating a new SS table, right? So it's creating a new SS table in the example. That, let me just move on to that slide. So if you see, I'm creating a new SS table here, so that means it's a major compaction. If you don't create a new SS table, you just read the data on the fly and return to the user, that will be a read only compaction. But this specific example is a write only, I mean this thing, uh, major compaction. So what happens is, while reading the data, compaction always happens, you cannot control it. Read only compaction will happen while reading the data, right? So that's not also a time consuming process, because it will happen for particular set of keys. You want data for one key, it will happen for one key only, which will be very fast, which will take milliseconds, couple of milliseconds, which is very fast. But when you do it on all of the SS table, which has millions and millions of records, then, and it is a kind of a write operation, in the major compaction, then only it takes much of resources. So read only you cannot control, but the major compaction you can do it whenever you want. You can control it, you can schedule it, and you can have the priority set and all that stuff. But the read one has to happen while reading. It has to happen. It's part of the operations. Once the compaction is done, is there a way to retrieve old values? No, that is, I mean, there is no way to retrieve old value. Even if compaction is not yet done, I don't think you can go back and select the old values. So Cassandra will not show you. I mean, from the Cassandra, you can go to SStable and do some stuff on your own. That's fine. But if you select the value from Hector API or say from CLI, you will see the latest value only. You see the latest value only. It won't show you the previous values. But you can go ahead and do some admin stuff on your own. Then it will show you. But if you being a normal user, if you want to see the old data, you won't be able to see the old data. Is major compaction scheduled out of box? No, you have to schedule it on your own. So you have to trigger it whenever you want. There are some consoles, like some UI part of it, that I'll explain you in later slides or probably in later modules. Then you'll see how to basically run the major compaction. You just have to click one button and you are done. Okay, so I will show you through, I mean, how it is done. So there is no way to retrieve the old values as such, but since, I mean, suppose you have three SS tables, you can always delete one of the SS tables manually, and then it will start showing the previous data. But that's not the like right way to do it, right? It may like mess up some other things. So but ideally, I mean, if you, the answer to your question will be, we cannot see the old values, but there are ways. You have to tweak it a bit, but that's not the usual way of doing it. It's an unusual way of doing it. Okay, any doubts further? So am I good to go? Okay, so there are no doubts. I'll go ahead. What are tombstones? So tombstones are nothing but they're analogous to soft delete. So if you remember, in RDMS world, you might have done soft delete, because deletes are an expensive process. I mean, wherein the space is not freed up and all the stuff, and you want to do the freeing up space once in a while. You just update the record saying some flag saying it is deleted or it's not the active record. So this is what we mean by a soft delete. So the data will not be deleted. It's just that when a user try to access it, it will not be shown, but the data resides in them in the backend in the physical devices in your hard disk. It will still reside. So a tombstone is nothing but a kind of a flag that we set for this soft delete functionality, saying okay, this column or this particular row, this particular row key has been deleted. So when you access the data from Cassandra CLI, it won't show you. It won't show you the columns that you have already deleted, right? So I know there is a again there is a constraint on space. Since we are doing soft deletes, this is a constraint, space constraint. A lot of space is being if you have a lot of deletes, then a lot of tombstones are being created and a lot of space has been wasted because of that. So that happens, but the compaction process that runs, it also takes care of the tombstones. It will clear the data, it will take care of the data that has been deleted, it will remove that also. So it will take care of two things, updates as well as the deletes, which is nothing but the tombstones in this case. Okay, that part is clear. So compaction will inherently clear tombstones as well. Can you roll back? No, we cannot. Manisha, we cannot roll back. There is no concept of roll backing in Cassandra. So that's when we said there is no transaction control. There is no commit and rollback in Cassandra. Tombstones are just created because it's very hard for Cassandra, the way it stores the data. It gets very hard for Cassandra to go back and delete it. And at the same time, to be efficient, to be very very low on latency, it's not possible to delete the record permanently. It takes time. So that's why we use tombstones. That's why Cassandra makes use of tombstones to become faster than the normal delete. Okay. So, but there is no rollback functionality. You cannot use it. There might be some. I mean, if you are a if you know the Cassandra code and all, how the Cassandra stores the data and all, you might go and create a you can write some custom code to basically remove tombstones. I mean, remove tombstone as in remove the soft deletes. Something you can do internally if you know the code. But as an end user, as a user of the DB, if you don't have the admin access and all, you cannot do it. You cannot roll back. Okay, so let's move ahead with the next slide. Okay, there's something I didn't cover. Let me go back. Okay, so there is something called garbage collection gray seconds. So Cassandra uses a setting called garbage collection gray second. This is the amount of time the server will wait to garbage collected tombstone. So the default value is 10 days. So after 10 days, the tombstones will be discarded if you don't run a compaction on your own. So if suppose there was no compaction for 10 days, so every 10 days basically garbage collector will run and try to clean the tombstones. So if you have so many tombstones in your application, if you have so many delete operations happening, you set this limit to be 1 day or so, so that at the end of each day your tombstones are discarded. Okay, so you can set the value. By default it is 10 days. So garbage collection gray seconds, we call them. So this is how the tombstone happens. Tombstone is configured this way. So we have the row key 1 first name, we last name, we have row key 3, we have row key 2, three records in Cassandra column family, and you want to delete row key 3. Okay, so what will happen is it will just maintain an internal flag. This flag it will maintain saying this row has been deleted. Okay, but it won't delete it. It will just maintain this flag. It will say, it will keep a tombstone red, this red brackets, that's it. It will say okay, this is there, don't delete it. This record is deleted, so if a user asks for it, don't return it. So but when compaction happens, it will remove this row. This row will be gone from the physical memory, physical hard disk. Okay, so this is how it happens while compaction. I have a couple of questions. Does compaction process create tombstones too? No, compaction in any way cannot create any tombstones. I mean, compaction basically deals with the clearing the data, just removing the data stuff, right? So why would compaction create tombstones? Compaction means the data that we don't need, it is already updated or is already deleted. We'll have to remove it. Okay. So what do we mean by discarded? As in, I mean, it won't be shown up to the customer, in the client, but yeah. So you have got it yourself. Okay. Okay. So what is the advantage of Tombstone? Is there no point in holding deleted record? So advantage is, while, so what happens is if you want to delete the record, you have to do disk seeks. You have to go to the disk and change something. And when it comes to interacting with the disk, right? When it comes to getting to the disk and deleting it, it gets very hard, right? It takes a lot of time to do that. And the second point, and second time, if you remember, we said our SS table cannot be changed. Our SS tables are immutable. That's what we said some time back, right? So if you want to delete a record which is part of those SS tables, then how will you do that? So there will be a tombstone created somewhere else that will say, hey, this record is deleted. So when you retrieve the data from SS table and you check it in the tombstone, it says this record is not supposed to be shown to the customer. Okay. And that's how the tombstones are made use of. So this is how the tombstones are used. So SStable is only write once. That's it. Write once and read multiple times. SStable you cannot change it. You cannot edit it. So that's why we create multiple SStables. So if SStable would have been kind of changeable, we could have changed SStables. So we would have created only one SStable only, right? We could have just created one SStable instead of four, because every time memory gets full, every time mem table gets full, we create a new SStable. Why so? Because existing SStable cannot be changed. That is the reason behind it. That's why the tombstones were introduced, to handle the scenario in all of the components like Commitlog and everything. Everything everywhere should be updated. That's why we maintain tombstones. Okay, guys. So how do we load balance the cluster? So how does the load balancing is taken care by? It is taken care by maintaining the partitioner. So we maintain a token saying data range 1 to 25. Okay, will go to this token, this node. Range 26 to 50 will go here. 51 to 75 will go here, and 75 to plus it will go here, right? So this is how the load balancing is done. So data balancing is done. This happens in a random. So the value that we are giving is 0, 25, 50, 75. It's a hash value. It's not the actual data value, because the data might be skewed. There is a way you can, there are two type of basically partitioners. There is a byte order partitioner which maintains the order, where you actually decides the range manually, and there is something called random partitioner which decides the data randomly. It decides on the basis of some hash calculated on the data. So that's why how it gets random. So it will randomly divide the data such that it will make sure the data load is same on all the nodes. So data in all the nodes are almost same, so that the reads happening can go to all of the nodes at the same level. Okay, this is how Cassandra balances the load in between. Okay, there is a concept of snitches. So what is a snitch? So snitch is basically to know which nodes are closer to me. So we won't cover snitches in detail here. We have a separate module to cover snitches. In the separate module we have discussed snitches a lot. We will go there and discuss it, but I'll just give you an introduction what snitches mean. So when it comes to bootstrapping, let's say bootstrapping or anything, or let's say bootstrapping, let's take an example of bootstrapping. So what has happened in bootstrapping? You have few seed nodes that you have declared. So let's say you have declared 5 nodes to be a seed nodes. So how does a new node will come to know which node is the closest one, or which node is the closest one, or from where the information that it needs to copy will be the fastest? How it will do that? So how it will be taken care of that? So we create a snitch. Snitch will basically, it will call a snitch to know which host is the closest to it. Snitch is used to know the host proximity, right? So it will have the rack information and everything, depending on which it will store the information. So there are different types of snitches. So there is a simple snitch which will tell you, like which doesn't, which is a rack unaware, which is a rack unaware kind of a snitch, which doesn't know whether there is a rack or a data center. Depending on the network, it will just tell you which is the node which is the closest to one. Probably it can give you the node sitting next to you in a ring format or something, or but it will tell you which node is the closest one, so that you can start reading from that node. instead of going to some other node. This node, reading from this node will be most effective. So that's what a simple snitch will tell you. There's something called dynamic snitches. So there are some clusters, there are some infrastructure setups which are dynamic in nature. For example, Amazon Web Service, AWS cloud that we have, right? It is dynamic. I mean, basically we have the VM setups on AWS and all that stuff, right? So the rack information and the data center information, it keeps on changing at the backend. So Amazon has basically created an EC2 snitch. It calls it a EC2 snitch. So EC2 snitch, you have to call EC2 snitch in case you have your Cassandra cluster maintained in AWS. Okay, and then this the third type rack inferring snitch, which is a rack aware kind of snitch, which is, I mean, you have discussed the network topologies, right? Replication strategies in is the same one. I mean, concept is same. Rack inferring, it knows there are different data centers. So what it will try to do is it will try to give you a host which is in the same rack or in the same data center. Instead of giving you a host which is in a different data center, you will prefer reading from a node which is in the same data center, right? So that's how the network will be faster, because you are running at the same area, same data center. So the network will be faster because one data center can be in India, other data center can be in US. So copying the data from US to India will take a larger time than copying the data from India to India, right? So this is how snitches helps you to know the host proximity. So what is anti-entropy? So anti-entropy is a kind of process which is used to basically do replica synchronizations. So suppose you have a data that is replicated across different nodes. You have one data, say the user ID is K Narula, and username is Kunal. First name is Kunal, last name is Narula, and the age is, say, age is 28, and let's say city is Bangalore. This is the data you stored. Now after a year you want to update the age to be 29. How will you do that? So how will it will be done? The first update will happen, first write or first update will happen on one node. The first primary node will happen, right? Depending on the partitioner. But how that change is replicated to other nodes? How does that is done? How this thing is done? How does the replication happen? Right? So in that case, what will happen is there's some service called anti-entropy. It will create the Merkle trees. Merkle trees are nothing but is a hash representing the data in a column family. It's a kind of a tree structure. It's a kind of a tree data structure you use. Hash tree map you use. It will create for a column family one Merkle tree. Then it will compare with the neighboring, like neighboring nodes where you want to have the, this thing, you want to have this thing, what do you call it, you want to place the replicas, right? So you will create the Merkle trees from each of the replicas and then compare, and wherever the difference is you will just replicate the difference, only that difference, because here the only age part got changed, right? So in our example only Kunal's age got changed. You have to basically replicate age only, the other stuff is still same, you can ignore them. So to just know what all the different attributes that you need to update among the different replicas, you will create a Merkle tree. Anti-entropy will create a Merkle tree which will compare it. Okay, so that concept is clear. So how does it compare, right? So now it will know there's a difference in age, and it will just sync up the age part from the primary primary copy to secondary copies. It will do the sync up, right? And anti-entropy is actually called doing major compaction also. You did a major compaction, okay, and then also you do the same thing. So major compaction also, you are basically sorting out things. You prepare a Merkle tree and you want to do the same thing onto the the other replicas as well. So during a major compaction, entropy will get triggered on its own, right? So this is how it is triggered through major compaction. And or you can trigger, I mean, I think it can be triggered manually also, but I'm not sure. But during compaction or during replication it gets triggered automatically. So anti-entropy service implements a singleton pattern. What does that mean is, So you cannot run multiple instances of entry entropies. So if you see, the complexity is involved here. So a particular node has its own primary copy, right? It stores the primary copy of the data. That primary copy might be different column families as well, right? And then it has a secondary copy that it stores, that comes from the node sitting next to that particular node, right? So there is a primary copy, there is a secondary copy, there is a tertiary copy, and every copy has a different types of column families, right? So the things get so complex, we don't want to run a multiple anti-entropy services, multiple instance of anti-entropy services. We run only one singleton pattern. There's only one service that run which takes care of everything, so that everything is made sure, everything is compared and replicated. Okay, so it defines the static differencer class, which is used to compare two trees. There is a class called differencer static. It's a static class. There is a functions available which it calls to. There are some static methods available in the static differencer class which it calls to basically get the differences, and it does a repairs and all depending on that. So the age part in my case, in the example that I told you, age part was something that was not syncing. It will sync up the age part only. Okay. So going to the next slide. So this is how the Merkle tree is prepared. This is how so it will see wherever the difference is, it will just go to the difference and do it. So suppose this is the column family name. Top hash is the column family. Let's say it is the row key. It says Kunal. Okay, first row key Kunal, and then it says the first name. Say something. It says first name, last name. So this was the user ID, first one Kunal. Say let's say K Narula or something, and this is the Kunal first name, and then this is the age. Same here for the different this thing for the different say different cluster, different node. It will have K Narula and first name and age. It will see the difference is there in age. It will sync up age only. Okay, this is how anti-entropy works. So let's now go back to the read repair that we missed. Let's go back to read repair. So what happens in read repair? So depending on the replication vector you declare, let's assume there are three replicas: replica A, replica B, and replica C. Okay, so you define your consistency to be high. You're reading some data from Cassandra cluster. You say my consistency while reading should be high. So what does happen in high consistency? Okay, so what does happen in high consistency? It will read the data from all three replicas. It will match the record. It will match the response. It gets back, right. It will match the response, and then it will return you the latest column, right. That's what happens while reading the data and with high consistency. So that part is clear, guys. So what happens while reading the data with high consistency? So there are three replicas. They might be out of sync. They are not synced. So you want to get the age. One replica has age equal to 28. Other replica has age equal to 29. The third has age equal to 28 again. But you are interested in the latest age, depending on the timestamp. So what Cassandra will do internally is it will get the three records from three replicas. Then it will compare the timestamp. Which one is the latest one? It will return that to the end client, which is this blue box here. So now there was a difference. Now there was a difference in the data. When will that difference be repaired? So while reading itself, while you are reading it, it gave back the response. Then only it will start. It will start syncing up the differences. So it read repair inherently then will call anti entropy function. It will call anti entropy service to sync them. So that point is clear, because you might be pulling one column, or you might be pulling more than one column also, right. So that's why we call anti entropy, because it will create a Merkle tree. You can have millions of columns, right, in Cassandra. So you can basically, probably client was asking for millions of columns to return. So it will create a Merkle tree, which is a hash representation tree, representation in hash, which will get the things faster. The comparison will be faster using anti entropy. So fine, why read repair calls anti entropy service. So this part is clear, guys. So any doubts, you can just ask me. So any doubts, guys? Just say yes or no. If in case you don't have any doubts, just say no. I'll just pause for a minute because we are almost done with today's lecture. So there is very little left, and I'll show you how SS tables looks like and all the stuff in a minute. I mean after that. So there is nothing much left. So probably I would encourage you guys to just ask any questions. In case you want me to repeat any topic that is not clear to you guys, I will happily do that. There are no issues with that. Okay, so question from Ranjit. What's the need to contact all three replicas for read operation? Ideally, one replica is contacted during need. Not necessarily, Ranjit. So if you see, the replicas might be out of sync, right? So there was some data that you have written on primary replica, okay, but that data is not replicated to other two nodes, okay. Now the read operation can go to any other replica. So the data which is not synced yet, which is not replicated properly, how will that data be accessed? So the read request will be fired on depending on the consistency that you give. Here I talked about consistency to be high. So consistency high means it will wait for all three replicas to respond back. So it will make sure the consistent data that is returned to the client is consistent. For that, it will have to contact all the replicas first. It will have to contact all the replicas first, and then it will get the data. It will see which one is latest, which one is the correct data, then only it will return it. So that's the need when it has to contact all the replicas. But irrespective of the consistency, if you give your consistency to be low, if you give your consistency to be lowest also, then it will also give the query to all the replicas. The replica which will be the fastest one, that will be taken irrespective of the whether it is the latest data or the consistent data or not. It will take the fastest one. So that is the difference between consistency level low and consistency level high. So that is the prime difference. So but it will contact all the replicas every time, so it needs to be the fastest enough in case of consistency to be low. But if consistency is high, it has to wait for all three replicas to respond back, and then it will compare the data, and then only it will return the consistent data. So that's the need we have when we want to get the consistent data. The data has to come from all three replicas. So there is one more question. All these are one-time configuration we need to perform as a job. Not really. I mean, you don't even need to worry about read repair and anti entropy. I mean, all this stuff is a kind of a maintenance. It automatically does it whenever required. There are a few things like compaction and all that you can trigger manually whenever there is. I mean, you have to maintain your a cluster. You have to do some maintenance activity. That's the same scenario with all the systems. Let it be a storage system, let it be any application. You have to do some maintenance activity with time to time. So here there are certain maintenance activities like compaction and all that you have to trigger manually. Your administrator will have to trigger it manually at some point in time, right? So certain configuration you do it at one level, and certain configuration you have to certain things you have to do it again and again. So Ranjit has a follow-up question. So got it. So there is the concept of Bloom filter has any role on contacting replicas in Cassandra. So Bloom filter by default is on, as you asked whether Bloom filter is on or off. So it is on. So while reading a data from SStable, that is from replica only. So it basically goes to first it goes to Bloom filter. So if you see in a replica, what do we have? In a replica, we have a key space, we have a column family, right? So for each column family, we have the Bloom filter setup for each SStable. So column family will have multiple SStables, right? Right. So for each SStable, we have set up a Bloom filter. So when you say I want the data, you basically hit a SStable only to get the data, either SStable or memtable, right? So most of the times you get SStable because memtable is very small as per the size. So mostly your read request go to the SStable. So each SStable has a Bloom filter associated with that. which you will go to Bloomfilter first. You'll say, okay, which SStable I need to query, which SStable my row key can be in. So you go to Bloomfilter first. If you get a negative response, well and good. You don't need to scan the SStable. You are out, and then you go to next SStable, right? So you go to as next SStable. You basically first query Bloomfilter. You say, Bloomfilter, what do you say? My row key is there. If Bloomfilter says yes, you will scan it. If it says no, then you won't scan it. Right, so that part is clear, Ranjit. Now how does bloom filter comes into picture? Okay, Ranjit, thanks for confirming. When we say replica, is replica is nothing but of a column family of SStable and commit logs. So both SStables and commit logs get replicated across different machines. Okay, so let's go to next topics. There are no more doubts. There is one more doubt from Manisha. How does query how does user query bloom filters? Can you use so you don't have to worry about it. Like Manisha, it is an internal process. Whenever you make a read request to Cassandra, whether you use Hector API, you use CLI, whether you use SQL, use anything, Cassandra inherently optimizes it using bloom filter. It's an internal optimization. How does Cassandra optimizes your read operations? You won't say, okay, give me this SS table or something. You'll say, give me data from this column family. You'll never say, give me data from this SS table. You'll say, give me data from column family. It is Cassandra which will do the tuning for you. It will do the optimization, saying, okay, this column family has 5 SS tables, and I'll use Bloom filter to make sure I do minimum reads. I do minimum scans. Okay. Yep. So there's something called SEDA. We call it Stage Event Drive Driven Architecture. So what does it mean? Is it's a kind of architecture being followed in almost all the concurrent models wherein we need concurrency and all. So I mean, in this model, the stages are divided into different stages. I mean, sorry. So different operations are divided into stages, and there's some events associated with the stage. So how does it happen? Is your write request, as you say, in case of Cassandra, it's divided into different stages, which will be write to commit log, write to memtable. Write to commit log will be one stage, write to memtable will be second stage, write to SStable will be third stage. Okay, so these are three different stages, and there is a different thread pool associated with each stage. There are no common thread pools. So when you start some thread on write operation, write stage, I mean writing to commit log, the first thread that will run is it will write the data on commit log, and that thread is free now. That thread is free. It doesn't care about whether the data from commit log is read to memtable or not. It doesn't care about that. There is second thread which will make sure the data is read from commit log to memtable. So what is the use of this? So suppose, as I said, you have written data to memtable, and memtable needs to be flushed to SStables, right? But somehow memtables didn't get resources to get flushed. There are some problems with the resources. There was some resource contention going on, and memtables didn't get resources to get flushed. In that case, Cassandra doesn't stop writing to a memtable. It will start the thread which will create a new memtable, which will be the active memtable, and will start writing to memtables. The previous stages do not get blocked because of the stage which is in the later point in time, which is getting hanged. So memtable is kind of hung because it's not getting dumped to SStable for some time, for few milliseconds. Fine, they might be delay for a few milliseconds or seconds only, not more than that. It won't go to hours. It will be seconds in case everything is good. So you have few memtables that are getting to be flushed, but the writing process doesn't stop because of that. If you have a same thread doing everything, same thread writing to commit log, memtable, and then flushing it, then unless and until you flush it, it won't be able to get a new write request. So if you have a thread pool of 5 threads, suppose at max you can get 5 threads. You can run 5 threads at a at a parallel. You'll be able to get 5 write requests only. And if something is hung, you won't be able to take more requests. But in this case, It doesn't happen like that. If it's a stage event driven, there is a stage and an associated thread pool with it. So it will make sure so the processes are running in parallel. So the while the mem table is getting flushed to SStable, commit log is taking more write requests. That is fine. That needs not to be stopped because of mem table getting hung. So that's the prime. That's how SEDA works. And SEDA is primarily used in all of the storage systems. Mostly all of the storage systems that basically like run on concurrent model and all. So this is how it is done. To make use of it, to how to implement this, we make use of Java util concurrent executor service. This is a class in Java executor service which basically implements this kind of structure. Okay, and a stage consists of three things. It's a incoming event queue. Yes, I forgot to mention there's an incoming event queue. There's some data has to be shared between one stage to another stage. So there's an event queue. Okay, so that will basically make sure the data is transferred from one stage to another. And then there is an event handler, as you said, event handler. And third thing is associate thread pool. So every stage will have its own associated thread pool. Okay, so now coming to the different managers and services running on Cassandra, there is something called Cassandra daemon running. So as we said, when we start a single node, we start a single node by saying Cassandra minus f. So it starts a Cassandra daemon Cassandra service on that node. So that daemon will control the life cycle of Cassandra service. The overall Cassandra operation will be controlled by that daemon. Okay. So then there's something called storage service. It contains the node's token, which is a marker indicating the range of data that the node is responsible for. There's a service running which will make sure what data this node is supposed to get, the primary copy of data, which is decided by the partitioner. So partitioner will inherently will be called from storage service. The partitioner is just a class. Okay, it has some logic, but it will be called from a storage service which will maintain the node token. If a node goes down or you add a new node, it is the responsibility of a storage service to get the new node token, to rearrange the key space, to rearrange the key range, in fact. Okay. Then the third thing is messaging service. As we see, different nodes talk to each other for different purpose. So to getting the replicas, to getting the heartbeat information, all that stuff. So so there are so many inbound and outbound messages which is taken care by the messaging service. Okay, so all the information that is exchanged between two nodes, it happens through messaging service. Then there's something called hinted handoff manager. So this service will basically manage the hinted handoffs internally. It has an hinted handoff thread pool separately for doing the same. Okay, so this is on a high level in terms of Cassandra management service.